Hello, everyone. Good morning. First of all, I would love to thank all of you for joining us at Data and AI Summit for the next few days. We are very, very excited to have you here. We're also very excited to announce some of the really cool product launches that we'll be doing over the next few days. But most importantly, we hope that you will learn something new, something that you can take back to your teams, to your organizations, to make them even more successful. My name is Akhil. I run the AI systems group within Databricks. This group is responsible for building products, tools, and helping data scientists, developers to build AI applications, whether they are classic ML applications or, as you can imagine, more recently, Gen AI applications like RAG or agents. In the next 40 minutes, I'm hoping to spend a bit of time to talk about Mosaic AI Vector Search, a new product offering that recently went GA, and show you how you can use that to build some really cool Gen AI applications. Before we get into that, I thought it would be good to just go through some of the basic concepts about vector search, things that anyone who wants to use vector search for Gen AI applications should know about. Most of you probably are already familiar with it, but I thought it would be useful to just do a bit of a refresher course. As you can imagine, for something like vector search, the first concept that's really important is vectors, or what they're commonly referred to as embeddings. Now, embeddings are nothing but a numerical representation of a data. The data could be an audio clip, it could be text, it could be video, but it's a vector that represents a point in an n-dimensional space. And you can choose how big a space do you want. Like if you imagine you want a 512 dimensional space, you can have a vector of length 512, and there is performance and cost implications to that. Now you can generate these embeddings in random. You can take the data, start generating random numbers, and that can be an embedding too. But obviously that will not work. And typically what people do is they train models, specialized models that can take data of a certain format and generate embeddings. And as you can see, the quality of the model that generates the embedding is really, really critical. Because if the model was generating random embeddings, you would have these points all over the space. But if you have a really good model, what they can do, and this is where the power of vector search comes in, is they can have a property that if you have two data points, which are similar to each other semantically, it guarantees that the embeddings, the data point in the n-dimensional space, is close to each other. For example, if you have a model that takes texts and converts them into points, cats and dogs will be similar and will be closer to each other in that space, and so with a banana or an apple. And this makes it very interesting because once you have these embeddings, finding similar objects, finding data points that are similar to a given query becomes a simple nearest neighbor problem. What you have to do is take a query, for example, find me all the cats, convert that into the embedding, same embedding that you use to convert your data points into things, and find all the data points that are close to it in the n-dimensional space. And there are a lot of algorithms, a lot of research that has been happening over the last 30, 40 years on solving this really hard problem. As it turns out, finding nearest neighbors is computationally an intensive algorithm, and people have come up with things like what are called approximate nearest neighbor algorithms, which don't guarantee that they will always find the nearest neighbor, but are able to do it more efficiently, faster, and still give you a good result. And that's why there is a trade-off between latencies and recall. In some cases, you really want your results to be accurate, and you're willing to give up latency because it requires a lot of computation. And in some cases, you may say, look, I just want 90% recall. So as long as you're giving me nearest neighbors which are close enough, may not be the closest, I'm fine with it, but please return my results in 5 milliseconds or 10 milliseconds. And when you're doing this search, when you're doing this nearest neighbor search, indexing techniques really matter. So you may have heard of terms like HNSW or IVF, and I'll talk about it a little bit later in the talk. But these techniques are really important because they are what decide how efficient it is for you to do this search. The last concept, which a lot of people don't often talk about is actually the database. So you have the embeddings, you have the algorithm, but you still have to build a database similar to a traditional database that provides you the ability to index data. It provides you scalability. It provides you performance and durability and governance. This is no different than what you would expect from a SQL database or relational database. But this implementation is as critical as your algorithm to find nearest neighbors as well as embedding models. The way to think about this is embeddings and how you generate them and the retrieval algorithm impact the quality of your retrieval. They are probably the biggest lever that you will have in terms of how good is the retrieval when you make a query and say, give me all similar objects or all similar topics. Embeddings and retrieval algorithm will determine how good they are. But the database will impact how performant it is, how secure it is, and also how easy it is to use. And that's the things that you have to evaluate when you're looking at different things. So like any tool, vector search is a tool, and we should know what it is good for, what it is not good for. Vector search is absolutely amazing at doing what we call semantic search. You give it a query, you give it an object, and say, give me things which are similar to it in a semantic way. It is particularly powerful when you're trying to do this over unstructured data, whether it is text, video, or audio. And this becomes very powerful because instead of trying to figure out how do you do traditional keyword search, how do you find similar things or misspellings, vector search takes care of that already. But it is definitely not good for traditional SQL-style database queries. A few times customers come to me and say, oh, we have some data in our Postgres. We want to run some aggregations. Can I use vector search for it? The answer is maybe you can. You can come up with some fancy algorithms to do it. But really, that's not the strength of it. You should always think of vector search as a tool when you're trying to process unstructured data and you're trying to do semantic search. And as it turns out, with the emergence of Gen AI technologies, this has become a must-have component when you're trying to build Gen AI applications. Some of you may not know this, but vector database is not actually a new technology. The first vector database came out as early as 1990s in bioinformatics. And they have been doing this similarity search on proteins, on audios and videos. But it's only after the emergence of large language models that people have realized that when you're trying to build Gen AI applications on top of your data, you need something like a vector search or vector database to reduce hallucinations and provide better context to LLMs. Otherwise, your LLMs are more likely to give you the wrong results. And some of the applications that people have tried building and deploying in production is RAG, retrieval augmented generation. Think of this as a chatbot on your enterprise data. People are starting to do semantic analysis and classifications. One of our customers is essentially taking a lot of the support tickets and comments and the forums from the customers and trying to understand what's the sentiment. What part of the product are people happy with, what part of the product people are not happy with. So to use one of these Gen AI application example, let's just go through a typical RAG architecture. RAG, retrieval augmented generation, is essentially a chatbot, a chat GPT on your own data. And it starts with actually taking your enterprise data. It could be your support tickets. It could be your internal knowledge management system. It could be your documentation. And you convert that text into chunks. You basically take long documents and divide them into smaller paragraphs. And use an embedding model. As I mentioned earlier, that you typically have a model that takes data and converts them into vectors or embeddings and store them in vector search. So when a user comes and says, I have a question, do people like Mosaic AI vector search? What a RAG system will do is convert that into an embedding using model, use similarity search to find relevant context and give it as prompt to a LLM and return the answer. And as you can see, in this architecture, vector search is a critical component which allows you to ground your application, which allows you to pass relevant context. Without this component, you will not be able to make sure that your enterprise data, that the data that is unique to your environment, to your enterprise, your company, is used to give the relevant answers. And while Mosaic AI platform enables you to do everything in this architecture, for example, we have model serving, which allows you to do LLM model. In this talk, since I wanted to focus on Mosaic AI vector search, the component that we allow you to do easily is the bottom half, where you can have your unstructured data in Unity Catalog volumes. It's a very easy way to store your data securely. You can use our data platform to process the data, as I'll show you in our demos, and then convert them into vector search, and then feed them into any application that you want. So some quick stats that I wanted to share. To give you some context, we launched public preview for vector search in February, and we went G about a few weeks back. And in the very short time, we have more than 1,000 plus weekly active customers actively using our systems to build GenAI applications. And some of these applications are really, really awesome. People are trying to use this to build agents that can book tickets for you, trying to build customer support chatbots. Out of the 1,000 plus, we have more than 200 large-scale deployments. Large-scale deployments are the deployments which are handling hundreds of millions of vectors and being used to serve production traffic. And the growth has been impressive. I think it speaks to as much about the power of this new technology that we're all excited about, but also how we have been able to scale a system where we are seeing a 400% year-over-year growth. Now, at Databricks, we believe that we need to make sure that we make it easy for you to get your business and company and organization successful. So we spend a lot of time talking to customers, even before we launch the product, but even after they launch the product. And we ask them, like, what are the criteria that are very important to you when you're trying to evaluate a vector search? It doesn't matter whether you use Mosaic AI vector search or anything, but tell us the things that are important to you. And was consistently these 4 things. Number 1, like any infrastructure that you expect, was scalability and performance. The questions they would ask me is, how many embeddings can you support? And this is the scale I want the things to work. What are the latency requirements? Do you want it to be sub-millisecond? Do you want it a few milliseconds? The second one, which personally for me was a little bit surprising, but actually is very important, was governance. The excitement about this new technology is immense, but people correctly so are also worried about, does this expose them to new areas where they cannot have the security and governance policies? The third one, which is one of my favorite, is just the ease of use. They were worried, particularly the data platform teams in companies, that, oh, we are going to be now stuck with managing yet another infrastructure and configuring it and making sure the teams can use it. And the last, but definitely not the least, perhaps even the most important, was the quality of retrieval. So the way it would work is people would start playing with the product, they will use it, but at some point, they will say, look, in the end, I cannot deploy my GenAI application unless the quality is good. And actually, you will see a series of launches in the next 2 days that is squarely focused on helping you improve the retrieval quality too. So we took these 4, and we wanted to make sure that we give you world-class, best-in-class product in each of these dimensions. So starting with scalability, a lot of the work that we spent on the engineering side was to make sure that we are able to build a scalable, performant system for you. It was optimized for high performance at low cost. This is one of the benchmarks that we did with some of the other vendors out there, and we've been very happy with how the customers have responded to what we have. It scales to hundreds of millions. It has low latency requirements. To be very honest, the job is not done, because while we can scale to hundreds of millions, there are customers who want to scale to billions now. And there are some exciting launches coming in the next few months that will allow us to get there too. But the response and the performance on the scalability of product is definitely world-class. The second one, governance. Good news, nothing new for Databricks. All of you have trusted Databricks with some of your most critical, most sensitive data. You have been doing a lot of data processing. But we wanted to make sure, as we build new products, that same trust, the same system that you're used to using, are also carrying over into vector search. So we designed it to be secure from the beginning. There were multiple layers of isolations, all the way from the network and the compute and the disk where the data is stored to be secure. We also gave complete control on the data to you, so things like customer managed keys. And I've also talked about my demo a couple of features where we allow you to take your embeddings and move them into anything. And the last one, which again is extremely popular with our customers, is native integration with Unity Catalog. Now, people are used to using Unity Catalog to do governance, to set up the security policies. And as you will see in a bit, when you use vector search, those same policies and the same workflows will also work automatically for you in vector search. The last one, the third one, ease of use. And this, again, we started with designing something that is zero overhead for all of you. We designed it to be serverless, which means there is no infrastructure to be maintained. We auto-scale to your workload, so you don't have to think about capacity planning, provisioning. You can just start up an endpoint, and we'll quickly switch to a demo to show some of this stuff. We have deep native integration with your lakehouse. So we have this unique API that we refer to Delta Sync API that I'll show you in a bit that makes it easy, trivial for you to create and update vector databases. Because one of the feedbacks that we got early on when we were developing the product was, I love that you have a vector database, but then the pipelines that have to update that vector database, refresh it, orchestrate it, was a painful part of their job, and we wanted to make it simple for them. As I mentioned, we also integrate with Unity Catalog, which makes it easy for you to also do the governance. And not just that, we have been integrating with other products that are part of the Mosaic AI platform, like model serving. And we will have some new products being announced and launched, like agent serving, where you can now start serving agents on our platform, as well as custom apps, where you can start building apps that can directly talk to vector search. So with that, nothing speaks better than a demo. I will take the risk and try to see if I can show you a live demo. So what I have for this demo is, what I did was I downloaded all the publicly available documentation about Databricks into a UC volume. What you see here is essentially a dump of all the documentation we have about our products in a UC volume. And as I mentioned, one of the first steps you want to do before you start using vector search is take your unstructured data and parse it and process it. And guess what? Databricks and the platform we have is actually really, really good at processing large amounts of data. So one of the things that you can see here is a very short notebook, is you can configure a pipeline which takes your source files, these are HTML files that we were storing at JSON, and convert them into essentially a data frame. This is what I did. I have a JSON parser. This could be any parser that you use. We have several cookbooks and templates that we have documented that you can use, modify, and change based on your data. But the point is that you take the data and you parse it into something that is more readable and clean up the data. And once you have the parsed raw documents, you have to chunk it. Chunking is essentially taking a large document and breaking into parts. And the reason you do that is because documents tend to have a lot of context. They tend to cover a lot of topics. And you really want to make sure that you get snippets, the most relevant context of a document. So in this case, what I did was I used a very simple chunking algorithm. So if anyone has used LangChain, they come up with some inbuilt chunkers, like text splitters. And what you can see here is I basically said for every document, I created a UDF, a user-defined function, which will take the document and convert them into chunks and store them. And once you take that function, you can essentially run this job, which I'll try to do it in real time. What this is doing is, let me just change it to a simple chunker. And so let's register this function. And then I try to chunk the docs. So this is essentially starting a Spark job, which takes your data from UC volume that we had passed and starts chunking it into pieces. As you can imagine, we are pretty good at processing large data. So what you can see here now is essentially chunks that of this type from the data. It takes the HTML document and is breaking into small pieces that we can now start embedding. Before you start embedding into vector search, one of the things that I mentioned was we have a delta sync API. So the thing that most of our customers do is you write these chunks into a delta table. Again, if you've used Spark, if you use our platform, and I think you're basically writing to a delta table, which I ran before the talk. And essentially, now we have a delta table that is essentially has your document path, your chunk text, and if I can, so this is essentially your table, which has these chunks. As you can see, these are some interesting HTML document. So now you want to index them. This is what you have. You have done the processing, which is more specific to your data set. You've cleaned up, but now how do you create the vector search? And that is actually very simple. The first thing you do is you create a vector search endpoint. Remember, we are a serverless system, so you don't have to provision clusters. You don't have to set up and figure out what should be the size of the cluster. What you do is you just go to compute, you go to vector search, and you create an endpoint. And you can say, I just want an endpoint with the name this, and you confirm. And that's it. You can also use our Python SDK that I will show in a bit. This will take some time. So I had already created the vector endpoint here, which you can see has some indexes. But the endpoint essentially becomes the URL that you will use to access those indexes. Once you have created those endpoints, creating an index is actually even easier. So if you go to the indexes that I created, if you remember, we had created this table that has chunk documents. In the UI, if you want to create an index, is you click on the Create button, create a vector search, and what you're doing essentially is creating an index. Think of this as a materialized view on top of your data. And you just have to give it a name. So I'm going to give it a name and say DICE demo, simple chunks. You have to pick a primary key. This is important because you need to have an ability to say when to delete or update a vector. So in this case, we had a chunk ID, which is a primary key. You select an endpoint. I showed you that we already had an endpoint that's created. And then you have two choices. One is you can say, hey, I just have raw text. Can you do the heavy lifting and generate the embeddings? I don't want to manage the rate limiting, the setup, the pipelines. In this case, let's do that and say, look, generate the embeddings for me. And I want to generate embeddings for this column. This column is what has the text, chunk text. And you give it a embedding model. Now, this could be any model which you're using in model serving. If you want to actually use Azure OpenAI, you can use external models to talk to them. You can have a model that you are hosting. It could be a custom model that you have trained yourself. It doesn't matter. The other cool feature that we just recently launched is you can also say, hey, when you're generating the embeddings, generating embeddings is perhaps one of the most costly operations you will do in this entire application. So you really want to make sure that when you generate them, you store them, because tomorrow you may want to take them and put them in another vector database. So you can just say, I want to sync the embeddings that you're generating back into a delta table. And as you can see, by doing this simple thing, what we are going to do is take your text, talk to the embedding model, generate the embeddings, not only index them into the vector database, but also write them back into delta table. And then you just do a create. So what this is doing, this simple operation is doing, is effectively starting a pipeline in the background that you do not have to manage. It's just running in the background and taking the data from delta table. It can also keep watching the delta table, by the way. If you have change data feed enabled, it can watch updates. So when you delete something in the delta table, when you update something in the delta table, we will reflect that back into the vector search and starts backfilling it. Depending on the data, it takes about 5 to 10 minutes. So I had actually done this thing before the demo. So this is the index that was created from the table. And if you look at the sample data, what you will see is this was the text that was being embedded, and this is the vector database that we generated from the table. So now this index, if you go back to the overview, this index is actually queryable on this endpoint. For example, we know that this data was indexed and was available in this endpoint. So let's go to the vector database, and then you can do the simple chunked index. And if you want, you can query the endpoint. So with a few simple steps, you are not only able to process your data, but also create an index, and it's ready for actually querying. So in this case, if I want to say, hey, can you tell me what is Mosaic AI vector search? What it is doing is essentially talking to the endpoint, talking to the index, and getting the relevant documents. As you can see, it returns them. This is giving you GenAI RAG reference architectures. It's giving you documentation about the vector index. Is created from a delta table. And this essentially means you're all set up to run. And given that it's a serverless system and auto scales, you're actually not just doing a POC at this point. You can also start deploying it in production. The same experience you can also do through APIs, because we know a lot of customers actually want this to do programmatically because they don't necessarily use the UI or they want to scale it up. And we have very simple APIs that you can use. For example, for creating the API, you just have to make a single call and say, hey, create this endpoint, and we will spin up the provisioning. We'll take care of everything in the background. And then once it's ready, you can start creating indexes on it. Similarly, you can create indexes. What I showed you in the UI a while back, which is like you just make an endpoint and start doing it. The other power of our product is there's a mode where you can say, hey, you should generate the embeddings for all my unstructured data. I do not want to deal with the complexity. But we also understand in some use cases, you may already have the embeddings that are generated and you have available, and you don't want to regenerate them. We can even index them. And if you go back to the catalog, let's take an example of a table where we have the embeddings already generated. So if you look at this table, by the way, this table is a write-back table. I told you that when we generate embeddings, we can also write it back to your delta table. But in this case, you already have the embeddings here. And you really don't want to pay the cost or the time to regenerate those embeddings. And if you want to create an index so that you can query it using vector database, you again go through a vector search index. You do something similar, Akhilji Dyer's demo, self-managed. You pick the primary key. You pick the endpoint. But in this case, you can say use existing embedding point. You can say, look, I do not want to have you regenerate the embeddings. And we automatically detect which column of your delta table has or can have vectors, and we offer this and say, you can do this. And then you do have to give the dimensions. I think in this case, it was 1024. And you create. And again, we are spinning up a pipeline that is essentially reading the data from your delta table and populating your vector database, but also making sure it is up to date. So if you have the option of continuous syncing, we'll make sure that as you're updating your data table or your pipelines who are processing your data change that data, we will update it into things. And you can query it like any other vector database. So that was about the ease of use. As you can see, it's very easy to use. It's very easy to get started. And given our serverless nature, the same setup can quickly go into production. You do not have to go through a different set of operations to do that. Now, once you have everything up and running, if you have already not gone to that stage, I can assure you at some stage what will happen is you feel good about the performance, the scalability, but the blocker for you to go to production is quality. You run some queries, you get some results, but someone is not very happy with the results, and you're like, OK, what do I do? And there are essentially 3 categories where you can actually improve quality when it comes to retrieval. One is just improving your pre-processing. This could be your parsing algorithm. You may be using a library to parse your PDFs, which is not really good. It could be a chunking, and chunking does impact what content it has, what content it needs to do. It could also be an embedding model. For example, you can use off-the-shelf models like I used in my demo right now, which is the BG, or you can fine-tune the model, or if you have data, you can actually build a custom models. And all of this you can do in Mosaic AI platform. And there are a lot of other sessions that will tell you how. And the last one is obviously retrieval algorithm. I mentioned the algorithm is really important. There are different techniques out there, all the way from LSH, which is the hashing technique, to inverted vector files, and HNSW. There's also hybrid search. As people have started building more and more GenAI applications, people are finding that the best results actually happen through combination of vector search, which is finding similarities in embeddings, but then also combining the results with classical keyword search. And we are going to announce it tomorrow, but vector search, as of yesterday, doesn't support hybrid search. And I'll show you in a bit how easy it is to use hybrid search too. So going back to the demos, so let's say that your quality is not very good. And when you're looking at your chunk docs, what you see is your chunk text has this annoying JavaScript, HTML pages, which clearly are impacting your quality. You're not happy about it. The customers, when they get the application, they're like, why are you giving me all this HTML? So what you want to do is you want to actually change your chunking algorithm. So what I did was I added what I call an HTML-aware chunking function, which is essentially extracting the text from the HTML. Now, you again can use any library, any system that you might build, or any open source. But what this effectively does is it's saying that, hey, can you extract text from the HTML before you start chunking it? And you again can register this as a UDF and run your pipeline again. So if you do this HTML-aware chunker UDF, and start the pipeline again. And this is essentially now rewriting your delta table, this time with extracting the text. And again, for the demo, I had essentially done this before. So the result of the job, which takes a couple of minutes, is basically it extracts the text and just stores that as chunks. So you can see the data is a lot more cleaner, which should improve your retrieval quality. Once you have done that, it again becomes trivial to create indexes on it. You can just use the same API or the same UI that I showed you, create an index. And since it's the same endpoint, you have to only change one parameter in your application. You just have to point to a different index, and your application is now suddenly using a better chunking algorithm. You can also use filtering to improve the quality, where you may discover that in your table, what's happening is when you query the vector index, you are getting data about Mosaic, but you are getting data about things like Lakehouse from a category called Lakehouse architecture. So what's happening here is we have a lot of documentation. We have documentation of vector search, about GenAI tools, but then we also have a set of documentation that talks about Lakehouse. And since it's a semantic search, what you're seeing is you are getting results from both. And what you really want is, I just want product information. So what you can do is you can add a filter, which is basically a SQL-style filter which says, return me results only from the product category called generative AI. This filter can be applied to any of your columns in your delta table. I chose the product name. It supports operations like greater than, less than, equal to. And when you run this, what this will do is it will give you the same results, but actually filter them based on the category you wrote. So now, as you can see, when I run this query, you only get the results from generative AI, which again can improve your quality because you are trying to guide the search specific to your domain. But this may not still be enough, because you may discover that, hey, I want to be able to make sure the content that you're generating still has vector search in it. Because of semantic search, sometimes what can happen in your documentation is it will start returning results which are related to vector search, for example, model serving, or data processing to generate embeddings. And what you can do, and this is the new feature that we're going to announce launching in DIAS, is hybrid search. But instead of getting you to do something new, different, do a lot of work, hybrid search is for free. It comes automatically, and all you have to do, if you want to use this, is add a parameter called query type. So if you are using vector search today, you can start using hybrid search by just adding a parameter called query type. And what this does on the back end is we will run vector search, get your semantic results. We will also run keyword search, the classical BM95 results, merge them, and return the results which can improve the accuracy of your retrieval. So in this case, when we return this, now this is ensuring that the documents that we return do talk about vector search, because it's also doing filtering based on keywords. So those are the things. Those are the 3 or 4 things that you can use to improve the quality. We also have some really exciting product launches that I mentioned, and sessions. If there's one session that I would strongly recommend to anyone who is trying to build GenAI applications or agents and also improve the quality of the agents, is the first one, which is the Mosaic AI Agent Framework. It's a new product that we're launching, and it'll make it very, very easy for you to evaluate the quality and also improve and apply the techniques that I showed you on vector search. But there are other things you can also do to improve the quality. Then we're also talking about model training, because fine-tuning and building custom models is very important. So strongly recommend, if you're not already registered with them, to attend them. And if the session is already full, please try and catch them in person. Then there's other things which are more general recommendations. I'm sure you have seen some of them, but just wanted to flash them as something that might be interesting to you if you're interested in vector search, RAG, or building GenAI applications. With that, that's all I had.